Assalamualaikum warahmatullahi wabarakatuh, and have a very good day. Today in this video, I would like to go through some FEA analysis using Solidworks, and we can compare this with analytical solution as what we have seen in the class notes. Okay, let me share my screen. All right. So you double click Solidworks if you have Solidworks installed or in the lab when you have access to the computer with Solidworks. So you double click that icon to activate or to start Solidworks. So when you have started it, it'll look something like this, and definitely something. And there is another. Okay, starting window, I would say. Anywho, if that is not available, you can start the new file by clicking on that, and you want to start with the part. Okay, what is it that we want to solve? So you want to solve this problem from the notes. So we have AB, the area, cross-sectional area of AB is 500, and this is 200. So yeah, we can try this thing. So we can create this thing, definitely. And this is 500 and 200. So this is 500 mm square, 200 mm square for the BC, and we have these materials with properties of Young's modulus or modulus of elasticity, 100 GPa and also 200 GPa. Okay, so let's see if we can get the same output. So we're going to start with the part. We have to build two parts. I have a feeling that I have done this before, but let's do this again. So once you got this, what should I do? So first of all, ensure that you are in the correct unit. So you go on the bottom right corner, click on that. I think we're going to use mmgs as our units. So meaning all the lines or all the dimensions are going to be in millimeters by default. So once you got that fixed, there's also another way to do that. Okay, I guess we can move on with that. So let's start with the sketch. So sketch, the cross section is just a square, a circle. So click on sketch, then so we got to choose one of the planes. So yes, we want to click on sketch. Click on that. Then we have to choose which plane. So you choose any plane. I'm gonna choose maybe right plane. That would be good. But any plane will be okay. Then you create with the circle from the middle. Create circle from that middle, and just like that. And then you use smart dimension to specify the radius, or in this case the diameter. So we have to do some calculation. So I'm gonna do open. You can open calculator. Calculator. What is that? Calculator. Scientific calculator. Scientific. Got this scientific calculator. So get to do some calculation. So we know the area is 2 pi r, or 2 pi d square over 4. I mean pi d square over 4 equals the area. In this case, the area is 500. So you want to find what the d is. So we have 500 times 4 divided by this one, pi, and you got to take the square root for all of this. So 500 times 4 divided by pi. Was that one. So in this case, the diameter would be 25.2. 25.2. So I'm gonna click there and change that to 25.2. Would that be enough? 2.3, let's say. 2.3. Okay. Then let's click OK on that. And then we want to create the solid. In this case, the length will be 400 mm. So let's go to feature, extrude, that one, and then this one you can move it, or you can change here to 400 mm. So 400, you can see that is the situation, and I'm gonna say yes to that. So for this AB, let's set the material. So material needs to be 100 GPa. Don't know what that is. So let's find something material with E of 100 GPa. So I guess material. Edit material. So in this case, not sure what to find, but we got to look at this one. So make sure it is this one is to be 100, 100 GPa. So 100 GPa is equals to this is 9. So about 1.0 times 10 to the 11, E11. So this one is 2. So this will be good for the second one. So let's try this one. This is 2. This one 2. This one, I guess 1010 is for the second material. I guess let's try with something aluminum alloy. Expand that about 1060. 1060. And think like 1 to the 10 to 11, E11. Not that, I guess. How about iron, ductile iron? This is almost it. Yeah, let's try copper, aluminum, bronze. So that's almost it. Not yet. How about brass? So this is okay. So this, I think I want to use brass for the first one between the member between AB. So let's apply that. So and close. So this change, the color also changed to match the material that we selected. Okay, so it's a brass. And I guess I'm gonna save this thing. Save this thing. Save or what? Save as. Save as. So where do I want to save this thing? So I'm gonna go to my folder. CE 25, and maybe under the slides. So save over here. So this is part AB. Part AB. Part AB. So you can put any name you want. So that's the first part. Then the second part, let's create another. So I'm gonna go to another new. Also a part. Same thing here. Change your unit, and then go to, so it's mmgs, then go to sketch, start sketching. I'm gonna choose the right plane again and use the circle. Click on that middle, create any circle, and then we apply the smart dimension. So we need to find or specify the right diameter for this thing. So in this second one, it's a smaller cross-sectional area of 200. So I'm gonna go to this one, and then use this square root, put on that. So 200 times 4 divide by the pi. So this one is about 16. I'm gonna put 16 or maybe just 15.996. 15.96. So let's change that to 16 or 15.96. 15.96. So I'm gonna accept that. Then go to features, extrude. So extrude this, and length of that part is 300. 300. So I'm just gonna cut to the chase and type 300 over here. Click here. So it is this long. Hit OK with that. Let's specify the material. Edit material. So I guess try iron base. So I guess 1010 steel, IC steel, AISI will be a very good one. So this is 200 GPa, 200 GPa. Apply that, then close. So it's supposed to be 1010 steel, and color doesn't, it's not that, it's just a gray color. So I'm gonna save this as part DC. All right, so we have these two rods. It's good. And then what I'm gonna do next is just maybe I can just close this thing. Can close this thing if I want, but I don't. I can just leave them. And the next one I want to create is an assembly. So I want to assemble them. Okay, assemble them. Hit OK with that. Okay, so the first part, AB, rod AB, you want to call that first. So let's call that part first. Okay. This one you do not click anywhere. Just click. You just hit the return key or enter key. Return key is for older computers, I would say. Long time ago. Some computers have return key, some have enter. But after some time, enter is the prevailing standard. All right, the next one, click on the assembly here. You want to insert component, so you want to insert the other component, which is part BC. So part BC, so this one I want to just click somewhere here. All right, so that will be enough. We have two. So this is the first one, this is the second. All right, then we need to do mate. So I'm gonna make this one to that one in terms of cylinder. So this one is good. So you click on the finish mate, but you can still slide it along that way. But they are concentric. You know that what that means. So it is concentric and sharing the same line of action or in the line. So the next one I want to this part, this surface made. Okay, you have to use your click and turn your roller on the mouse, and you can zoom in with the roller of the mouse and click on that one, so they will match or mate. Then you click the right button And then I guess that will be all that you need in terms of the assembly. Okay. All right. So I'm gonna click on the OK button, which is the right or correct, meaning that we are finished with this assembly. So now we want to do the simulation. So we will have simulation, which is the uh, analysis, FEA analysis, stress analysis, then also the flow. But let's focus on the simulation. So click on that, new study. So let's call it static 1, that's fine. Just hit OK with that. So the first one, you want to determine the fix. So I'm going to click on the fixture, add a fixture on the right pane. This is the pane, simulator advisor. Click on add a fixture, so you turn around a little bit like that, and maybe zoom in on that. So this is the part that you want to fix. So click OK on that. Okay, that is fixed over there on that one. So that part is cantilevered to the wall. And over here we have that 60,000 Newton force. So external load, okay. So I'm gonna add a load, and let's choose on the left plane. We want to choose force, and click on that one. So our force here is a pulling force. Is going outward from the wall. So 60 kilonewton, 60,000 Newton. So I'm gonna put in the value 60,000 Newton or 60 kilonewton, and reverse the direction. Like that. Then I'm going to click OK for that. So we have the force, we have a part that is fixed. Then you can run the simulation, or you can see the mesh, but I guess I'm gonna trust the mesh. So I'm gonna click on run here, click on run the simulation. Okay, so displacement. So here we can check on displacement here, and this part over here, so we can try to see what those values are. But it is about, this is in mm, so times 10 to the power of -1, so meaning this is 0.935. So if I 0.93 is the answer lah for this part on C. That is the maximum. So that part seems to be having that thing, that value, the maximum displacement. Can we see the result there? You plot your result. Probe. I can use probe. Okay. That one is having this much, 0.935 millimeters. So how about over here? So that one is 0.468. 0.468. So if you look at the calculation here, so at the very last, which is point C, this is the displacement, which is this is in meter, but if in millimeter, so you times that by 1000. So 1, 2, 3. So it's going to be 0.93 millimeter. So the answer will be over here, 0.93 millimeters. Okay, but if you do the calculation using 1D, one-dimensional FEA, with two elements, we have two elements, one between AB, and then the other one, the second one will be between B and C. So if you follow this this method, you will finally get the displacement to be this one. This is 0.93 millimeter, and the top one at point B would be 0.48 millimeters. So here it is reported 0.68, 686. So a little bit different from what is calculated by hand. All right, so I'm gonna click OK with that, and we can also look at stress. Stress. Again, we can use our probe. So over here, the stress will be 3. What is this? 300 megapascal. So this is in Pascal. So over here is 300 megapascal. So I'm changing it off on top of my mind, the unit. And how about there? So there is about 72.9 or 73 megapascal. 73 megapascal. Okay, so if I look at this calculation, so this one is correct, but this one is a bit different. See where I went wrong. 0.00048 divided by 0.4. So 1.2 times 10 to the power negative 3. 1, 2, 3. So this one should be correct. So this one times 109. This is 120 megapascal. How about if I put the probe here? Come on. That seems to be like, but this one is about 110, 110 megapascal. So yeah, I guess you can find 120 somewhere here. Uh, okay, so definitely we can find that somewhere. Okay, so many things shown here. So how about the this one is about 120 right on top there. So yeah, the location will give you different readings. So I guess the highest reading will be over there lah for this one. So location, whether you go up out from the center of this body, because in the center there is no it's like middle ground. But if you go up, this thing, uh, or you go further from the center, your values will be increasing or decreasing depending on the situation. Okay, so I'm gonna click OK on that, and yeah, so I guess you look at the equation here. So maybe this one can give some to probe. That is 300 all the way top here. Okay, so yeah, over here, I guess over there is 300, and over here is 120. So maybe okay. So here can use snipping points, I guess. Okay, so I put over here and compare, put it, just report it. Yeah, and maybe I'll put in the link for this exercise and oh, for this video, so that you can refer it in preparation for the tests or whatever project that you want to do using this thing. So I guess the answer is pretty accurate, and it agrees with hand calculation, if you use finite element, and also if you use mechanics of materials. So this mechanics of materials and also the FEM or FEM are two different methods and two different ways of doing the calculation, and also and then you can also compare it with the implementation using computer. And in the test this time, I want you to always to also use this one and report your and probably you have to also show if your calculation agrees with this value. And in this case, I would say it does agree. Between AB, you expect to have 120, and for BC, you expect to be 300. So you take somewhere along the two edges, so along AB and along BC. So don't go too too near the edges, but choose somewhere in between. Okay, I think that's about it for this video, and I wish all the best, and hope you can follow uh, this lecture perfectly, and we hope you can do well in the test. Assalamualaikum. Have a good one.